So in my previous video, I discussed that tree-based models have high variance or they overfit the training dataset very badly. And I'll be discussing one way to fix this, and that's called bagging. So let's first briefly recall what it means to overfit the training dataset or to have high variance, right? So let's say you have a set of some training data points. So as we discussed previously, you can construct trees that give you zero error on this training set. So you will exactly fit each of these training data points. And a possible tree can look like this. But if you now try to evaluate the performance of the model on a new test point, let's say X, then the performance of a tree model could be very bad. So this is what we are referring to as overfitting, and this is also referred to as having high variance. You can also understand it in a different way. So let's say this whole box represents your training dataset D, and you divide this training dataset into two parts, D1 and D2. Let's say you train a tree-based model on D1, call it T1, call this model T1, and then the other model, let's call it T2, which is only trained on the dataset D2. Now, because trees usually have a high variance, T2 will be very different from T1. So T2 might look something totally different than T1, and if you compute the performance of the two models on a test set, the results will be very different. And this is not desirable, right? So if you have high variance or if you overfit the training data set, then your performance on a test set degrades. And you would like to fix this using something called bagging. So bagging is an ensemble-based approach where you take several trees. So in the end, you'll have several trees which might look as follows. This is one tree, then you have another tree, then you might have another tree, and somehow you will combine these different trees, all of which are weak. So all of these trees are weak learners, meaning as a standalone model, they do not perform very well. But this combination, where we've combined the different trees together, this will be a strong learner. So this combination that we will eventually have will be a strong learner and will not have the overfitting problem that each of these individual trees had. And let's get into the details now. So the idea is that taking average of uncorrelated quantities results in lower variance. Let's assume we have n independent random variables. So z1 to zn are our n independent random variables, and each of these random variables has a variance of sigma square. Then if you take the average of these random variables, the resulting variable z tilde will have a variance of sigma square over n. So inspired from this observation, what we would like to do is create n different, so we want to generate n different trees, each of which will be a weak learner, and then take the average of those trees. Now, how can we do that? One way could have been that we would have partitioned the entire training dataset into n parts. So we could have taken the entire training dataset and partitioned it into n parts. And for each of these n parts, we could have trained separate trees and then taken an average. But that's usually not possible in practice because we don't have enough number of data points. So what we do instead is something called bootstrapping. So bootstrapping would help us generate n different data sets without having to partition our original training set. So here is how bootstrapping works. So what you do in bootstrapping is that you take a certain data set, maybe this represents your data set with certain number of data points, and then you keep on sampling this data set with replacement. That means if in case you sample this data point here, then you put it back into the dataset so that it can be sampled again. And via this continuous sampling with replacement, you can construct n different datasets out of this one single. So with the help of this continuous sampling with replacement, you can create n different data sets on which you then train your models. So here is an example. Let's say you have 4 different data points. So 1, 2, 3, 4, and we want to generate we want to sample 2 different data sets out of it. So n is equal to 2 in this case. So the first time we sample from this data set, maybe we get the first data point. So this first data point would be 1, and then we put it back into our data set. Then in the next sampling we choose 1 again, then we sample it again, then we choose 2, and lastly we choose 4. So this collection of 4 points will be our first data set on which we will train a tree model T1. We repeat the same thing again, and maybe this time we collect 0.2, 0.2, 3, and 1. And on this data set then, we will train the tree T2. And finally, as we discussed earlier, our bagging approximation would be T1 plus T2 by 2. So one thing that I didn't really discuss till now is what does it mean to average trees. So what does it mean that we are averaging these trees here? Here we need to make a distinction between regression and classification. So you have 2 cases. So for regression, averaging is straightforward. Averaging simply means that to take or to compute the prediction at some input feature x, we just average the values of the different trees that we have constructed. Okay. For classification, things are different because taking an average doesn't really make sense. So what you do is rather a majority vote. Okay, so in this case, in this particular example, if both T1 and T2 provide us with a class label 0, then obviously T tilde will be 0. If both of them are 1, then T tilde will be 1. And in case both of them, and in case one of them is 0 and the other one is 1, then T tilde could be any of these. We just choose one value randomly. Or one chosen randomly. So once we have these n different data sets, the next question, and we've constructed our bagged tree model T tilde, the next question is, how do we compute the error resulting from T tilde on a validation set? And this is done with the help of so-called out of batch samples. Let's say we have n different data points in our data set. So this is our data set with n different data points. So this is the ith data point, and we continue till n. Now from this data set, we have using bootstrapping, we have sampled n different data sets. So D1, D2, D3, so on up to Dn. So for this ith point, then we will try to find the data sets that do not contain this point. So let's say D3, D7 and D10 don't contain the ith point. So once we have these sets, right, we will compute the error resulting from T tilde on these data sets. So we will compute the error from T tilde, that's our bagged tree model on D3, D7 and D10. So this would give us 3 different error values, and we would take their average. So this average, let's call it E3, E7 and E10, and let's take the average of that. So this average then provides us with the error at point I. Okay, and once you have this error at point I, you repeat the same for different values of I. So the final error value that you report as the test error for this bagged tree model T tilde would be the average. That's a sum over the n different error values divided by n. So that's just the average of these error values computed on all the different data points in your original training set. Now this might remind you of something called the leave one out approach. So in the leave one out approach, what you do is, if you have a training data set, you take a particular point, you exclude it from training, and you train the model on all the remaining training points. And once you've trained the model, you compute the error on this left out training point, and you do the same for each different training point in the dataset. And then finally, taking the average of these errors gives you a representative error value. So this is very similar to the technique that we discussed here, and one can actually also show that if you sample a large number of data points, a large number of data sets. So if n is large, then actually this technique is the same as the leave one out approach. Okay? One correction I need to make is that this n is incorrect here. This should rather be m, where m is the number of training points. So we have m different training points, and we have n different samples of training data sets constructed from these m different training points. Okay, so we need to remember this. So this average, we are taking over the different training points and not over these different training data sets. So before moving forward, let me remark on a few crucial properties of these bagged decision trees. So first of all, if you remember from my last video, these trees that we constructed, that we are averaging t1, t2, and so on up to tn, each of these trees were explainable. So you could easily look at the diagram of a tree and explain why certain decisions were being made. That's not the case for the averaged tree t tilde. Okay, so as soon as you average these different trees, you lose explainability, but you can still recover some explainability by either linearization or using other types of techniques that can help you explain why certain decisions are taken. So that's the first point. So you lose explainability, although you do gain, and quite substantially, you do gain performance. If you remember, the reason we were averaging these trees was to improve the generalization error or to reduce the variance, and that's something you achieve to a very great extent. Second of all, so how do you choose the value of n? How to choose this value of n? That's the number of trees you want to average. So this value of n is we have a lot of freedom when it comes to choosing n. So if you plot error with respect to n, we realize that the error initially drops as you increase n, but then it just stagnates. It does not go up again. That means you can choose a reasonably high value of n, and you do not fear overfitting. So even if you choose a very large value of n, there is no overfitting. So what we do in practice is we slowly increase n, and as soon as we see that the error is stagnating around this point, right, we stop increasing n any further. To have the maximum benefit from bagging, you would like these trees to be as uncorrelated as possible to each other. Whenever there is some correlation, you won't get the maximum benefit out of variance reduction via averaging. So to handle that, there's a technique called random forests, or it's rather a model. So we'll discuss the random forest model next. So let us first try to understand how correlation between trees arises. So let's take the following example. Let's say we're trying to predict cost of cars using two predictors. So one is the manufacturer, and the other feature is something that's very uncorrelated to the price of the car. We can set this to be the precipitation level on a certain day. Obviously, you can't use precipitation level to predict the cost of a car, but the manufacturer of a car, this is a very strong predictor of what the cost of a car could be. Right? So when you have such strong predictors, what happens is each of these different n trees will place a lot of weight on this one particular predictor. And when you do that, because each of these trees are treating this now, because each of these trees are placing a lot of weight on this predictor, there will be correlations. Right? And as soon as you have strong correlations, then averaging does not really give you a lot of benefit in terms of variance reduction. So that's where random forest comes in. comes in and says, before fitting the tree, we first randomly sample a subset of the features and ignore all the others. So here is how this works. So let's say you have 4 predictors, x1, x2, x3 and x4. And in your first iteration, you sample a dataset D1 via bootstrapping. So now before fitting the tree T1, you would select a subset of these 4 features. Let's say you select x1 and x2. And then using these 2 features, you would fit T1. In the second iteration, where you sample D2, you will sample the features again, and this time you might sample x3 and x4. This will give you another tree T2, and so on. And when you have these different n trees, you will then average them, and this will provide you with the prediction. So the averaging remains the same as before, just the way we construct these different trees changes. And what we have done here, by randomly choosing a subset of the feature set, is that we are not allowing these separate trees to put a lot of weight on one particular feature. So if x1 was an important feature, so let's say x1, which I can mark it here. So if x1 is a very important feature, like manufacturer was in this case, then x1 appears in the case of T1, but it doesn't appear in the case of T2. So T2 will not put a lot of weight on x1. And by doing so, it will be heavily uncorrelated to T1. And since there is significant uncorrelation, averaging will provide us with variance reduction. So that's what random forest does. Okay, and how do you choose how many features you should sample? Usually the number of features you sample, which is denoted by m, is of the order of square root t, where t is the total number of features. So this value of m usually works for most of the cases. Now there are cases where you might want to select a smaller value of m, and this is where you have an extremely large value of p. So if let's say p is of the order of 10,000, then square root p is of the order of 100, right? But the number of important features out of these 10,000 feature sets are just 10. Okay, so it's possible that of the order of 10 are the number of important features. Now in this case, even if you set m to be square root of p, you will have enough important features. You will be sampling a large number of feature set, and each of this feature set will have these important features with high likelihood. And therefore you will not get the benefit of uncorrelation that comes from random sampling. So in this case, you would like to reduce the value of m. So this is the special case where this square root p heuristic doesn't necessarily works, and you might have to reduce the value of m in order to gain benefits out of the random forest algorithm.